Welcome back, everybody. We've been talking about a force of a magnetic field on a charge, but now we're going to be talking on a current carrying wire. You're going to notice it's pretty similar, and it's going to be a little bit easier because we don't have to think about positive charges and negative charges anymore, just which way the current is going. Okay, so we're going to use the same kind of right-hand rule as we did with the charge, but this time we don't have to think about flipping things if it's negative or anything. So a current going through a magnetic field will act in the same way as a charge. Again, we can use the right-hand rule, and this time we don't have to worry about negative and positive signs. So again, which way your hand goes is the current, which way your thumb is the force, and which way your fingers point perpendicularly from the movement of the current is the magnetic field. All right, so let's do. Oh, and let's look at the formula for this. To help us understand it a little better. So force of magnetic field on a current carrying wire formula. Okay, so the force of the magnetic field from the magnetic field is going to be equal to the current, how strong the current is, the length of the wire, how long the length of the wire is, and the magnetic field, the perpendicular part of it. We should know F is symbolized as force, I symbolizes currents, which is amps, L symbolizes length, which is not meters per second. That's just going to be meters. And B symbolizes magnetic field, Tesla. Okay, and this is the formula for it. The force of the magnetic field that it feels is going to be the current times the length times the magnetic field. And you can manipulate it in all these other ways algebraically. All right, let's do some examples. All right, let me move this. Alright, an electrical current is moving to the right and is going through a magnetic field that is coming out of the page / screen. Which direction is the magnetic force going to be pointed? Okay, so magnetic field going out to the right. And then the magnetic field is pointed out. So that means I'm going to flip my thing, point my fingers outward, going like that. Which means my thumb is going to be going straight down. And that's what we have. It's going to be going, oopsies, it's going to be going down. Right? Moving on. A 0.5 meter wire is carrying a current of length of 28 amps that is moving to the right. The current is going through a magnetic field that is going to the left with 18.2 Tesla. What is the magnetic current force on the current? Okay, so let's look at this. We know that the force is equal to ILB. Current times the length times the magnetic field, perpendicular. And then the current is 28 amps. The length of the wire is 0.5 meters. And the magnetic field is 18.2. Okay, so you might be putting this in and then thinking this is it. But there's a little bit of an issue here. We should know that the magnetic field is only going to be producing a current if it is perpendicular. And what we see here is the current is going to the right, magnetic field is going to the left. And if we try to do that with our hands, we're not going to really be able to do that. That's not going to work. It's not perpendicular to each other. So where's the force of magnetic force on the current? It's just going to be 0 because the current is not perpendicular to the magnetic field. All right, moving on. An example of this that shows 2 examples. They're pretty cool, so watch it if you can. Example number 6. A 0.2 meter wire is carrying a current of 42 amps that is moving down. The current is going through a magnetic field that is pointed into the screen with 18.2 Tesla. What is the magnetic force on the current and what is the direction? Okay, so let's just kind of figure it out. Force is equal to current times length times the magnetic field that's perpendicular. So that's going to be 42. Length 0.2, magnetic field 18.2, and it is perpendicular this time. Current is going down. Let's do this as down, and then this is going into the page. So you can see it's perpendicular, 90-degree angle. Okay, and then let me put this into my calculator. 42 times 0.2 times 18.2, 152.88. 152.88 newtons. Okay, and what is the direction? Okay, so let's do this. It's going this way. Oops, let me stand up. Sometimes you're going to have to get a weird angle, so going this. And then we're pointed into the screen, so it's going to be like this. And then we can see my thumb is pointed to the right. Okay, So 152.88 newtons to the right. Alright, moving on. A wire is carrying a current of 42 amps that is moving into the page. So the current is going into the page. And the current is going through a magnetic field that is going to the left with 0.91 Tesla. If there is a magnetic force acting on the current of 23 newtons, what is the length of the wire? Okay, so let's do that first. Force is equal to current times length times the magnetic field, but this time we're looking for the length, so let's manipulate this. Length is equal to force divided by current and magnetic field. So length equal to force 23, current, which is 42, times magnetic field 0.91, and then this is going to equal 23 divided by 42 times 0.91, 0.6, so 0.6 meters. Okay, what is the direction of the magnetic force acting on the current? Okay, so magnetic field is going, the current is going into the page. The magnetic field is going to the left. Okay, that means the current is going to be going straight up. So up. Alright, moving on. A 0.4 meter wire is carrying a current of 37 amps that is moving down. The current is going through a magnetic field perpendicularly. There is also a magnetic force of 12 newtons acting on the current, pushing it inside the screen. What is the magnitude and direction of the magnetic field? Okay, so let's first find the magnitude. Force equals current times length times magnetic field. What are we looking for? What is the magnitude and direction of the magnetic field? Okay, so we're looking for B. So manipulate this a bit. B equals F divided by IL. Magnetic field is going to equal to force, which is 12. Current, which is 37. Length, which is 0.4. Let's see. 12 divided by 37 times 0.4. 0.81 Tesla. Okay. But we need to now know what is... Okay, so let's see what the direction that it's going. So we can see the current's going straight down. Okay. And then we know that the force is going to be pushing it inside the screen. So it's going to be like that. That means the magnetic field is going to be going to the left. Okay. So we have 0.81 Tesla to the left. Okay, so I'm hoping this makes more sense as you're doing all these problems. It is confusing at the beginning, but I'm hoping it makes more sense. That's pretty much it. Next time we're going to be doing some harder bit problems, but I'll see you with that. Bye guys.